All right, so here we have the second video for measuring energy changes. We're going to be looking at enthalpy changes and the direction. Now keep in mind that direction is going to be usually towards lower stored energy, because everything goes towards disorder. So you want more simple molecules, less complex, so on and so forth. And so therefore we're typically looking at an exothermic reaction, though we can do this with endothermic reactions. Looking at an exothermic reactions, as we saw with an enthalpy stability diagram, we can see that the products are more stable than the reactants. And the reason being is that the products are going to be a lot more simple, just in complexity. They're going to be more simple bonds, so on and so forth, more simple IMFs, whatever it happens to be, they are going to be more stable. So here we're going to draw a stability diagram. So in the stability diagram, we're looking at your delta H. All right. So if we have hydrogen, gas, and oxygen gas, right? When we react these two together, we can go in a couple of different routes. Okay, what you would expect, you're like, oh, guess what? H2 plus O2, that's going to make water. Yay! Right? So we have H2O. And H2O standard state is liquid. And you are going to have some oxygen left over because we need twice as much hydrogen than oxygen. So we have half an oxygen left. And so remember in Brinkelhoff's, so O2s, H2s, so on and so forth, we can use this half value to say half of that Brinkelhoff because they're identical elements. So keep that in mind, that is the only time we can actually use 1/2 as a coefficient. Now, there's another way here. Sometimes when you react H2 and O2, you get a hydrogen peroxide as well. And that is a liquid in its standard state. All right, so here we have different processes. So if we have H2 plus O2, that could potentially make H2O2. When H2O2 decomposes, it decomposes into water and oxygen. But H2 and O2 can also react to go directly towards water as well. But because we're looking at stability, so H2 and O2, as we know, are very volatile. They're very reactive. They have a lot of energy. And so they will go through and react. When they react and make H2O2, H2O2 is a little bit more stable. And so we say this is stable relative to its individual elements. But because it can also break down, it is unstable relative to its products. And the products are H2O and 1/2 O2, which could also be the products of H2 and O2. So if we go through and look, we say our elements are going to make H2O2. That is going to have a value of delta H1. When H2O2 decomposes into its products, that's going to have an energy value of delta H2. And so those two values need to equal what if we took those individual elements and went directly to those products. So that's going to be delta H3. And that is what we're going to be looking at when we look at Hess's law, is the fact that all this needs to equal each other. And because energy, again, going back to the law of conservation of energy, it can't go one way, or it can't just disappear. First, we're going to look at the heat of combustion. It's a long definition. I apologize. So this is the standard enthalpy change of combustion. Remember in the previous notes, that theta symbol means we are under standard conditions. So 100 kPa, 298 Kelvin, 1 mole of a solution, if that is what we're looking at. When we're looking at different forms of heat change, we are going to provide a symbol like C for combustion to let you know what type of delta H we're looking at. So what does this look for? This is the enthalpy change for complete combustion of 1 mole of a substance in its standard state under standard conditions. This means there's going to be excess O2 in this reaction. So complete combustion is what we are looking at. We are assuming, making a huge assumption, that complete combustion is going to occur. When we are running these reactions, we set up a calorimeter, and these can look different based off what type of reaction you're running. So let's say we're going to run a combustion reaction. What this is going to look like. You are going to have your combustion chamber. So this is what, and we do not have one of these, and so this is a huge error for us. This is a drought shield. So it's trying to keep as much energy in the system as possible. All right, because we're doing combustion, we are going to have a burner. All right, so this is our burner with fuel. We're going to light that fuel. As you can see, the fuel is an enclosed container, so it's not just evaporating to the atmosphere. Then above that, we're going to have a beaker. In that beaker, we are going to have water, or a container of some kind, I should say. All right, in this particular instance, this container is going to be a copper calorimeter. We use aluminum cans just because we don't have a copper calorimeter. All right, in here is our water, so we are transferring energy to our water. We are going to have a thermometer submerged in that water. And so that no heat leaves the water into the system, on top of it, we are going to put an insulating card. All right, so preferably, this would be the ideal setup. What can we have? We actually have a burner. We use a crucible so it is open to the air with the fuel in it. We have water sitting in an aluminum can, and we do not have an insulating card, and we don't have a drought shield. We do the best we can, so we have a lot of air in our own personal setups, but this would be an ideal closed situation. So since the burner is giving off energy, it is burning, right? And that fire is really close to that copper calorimeter. It's going to heat up that copper calorimeter, and that copper is going to pass that heat onto the water. And so by measuring the change in the temperature of the water, we can make a direct correlation to how much energy that fuel is going to give off. So we're going to assume all heat is absorbed by water, and that's really a major assumption. So when we're looking at this, we're going to look at the heat change of the reaction equals the negative heat change of the water. We cannot directly measure how much energy is given off by burning a fuel because it's on fire. It's not going to happen. But we can measure the heat energy in the negative water. So what this looks like is you are going to have your delta H of your reaction. So you're going to have the mass of the reaction. You're going to have the specific heat for your compound. You're going to have and assume the temperature change of the compound, so on and so forth. So we have this MCAT, and it's going to be negative MCAT for water, which we can directly measure, so on and so forth. So if the delta H for the reaction is negative, right? Because this is negative water, you're going to have a delta H positive for water. This means the temperature of the water is going to increase. If the temperature of the water is increasing, it is absorbing energy from the combustion. So that means the combustion reaction is exothermic. So you have to look at these relationships and walk yourself through the process. All right, if we calculated delta H positive for our reaction, that means water had a delta H negative. That means temperature decreased for that water. So that shows that the reaction absorbed heat from the water, and that is an endothermic reaction. This second one does not occur with combustion or neutralization reactions. We will see an instance where it can occur. As discussed before, the unit is kilojoules per mole. So let's look at how we can do this in a calculation. So we have a mass of our water, and that is 200.00 grams. We have our temperature change, and that is positive 13.00 degrees Celsius, because that's what we directly measure in. And we have the mass of the ethanol that we burned. Okay, so we're going to do these in a couple different steps. And these are the problems that students get really confused on because they may be worded differently. Really read the question, which is why we give you ample practice. The first thing you want to do, step 1, you want to calculate the moles of fuel you're going to burn. So remember, when you do this, you are going to have your mass of your ethanol over the molar mass of ethanol. So remember this calculation setup that you have done previously. So we know we are reacting 0.45 grams of ethanol in the reaction. The molar mass of ethanol is 46.08 grams. Remember, you go through, you divide all the atomic masses of the elements in the compound, add them together. Divide the two numbers and you get 0.00976 moles of reactant burning. Okay, so now we know how much we're going to burn. The second step you want to do is you want to calculate the heat produced. Remember, the only thing we can measure in this is the change in the water. So this is actually delta H of the water. So if we have our heat change of water equals the mass of water times the specific heat of water times the temperature change of water, we can figure out how much energy the water either absorbed or lost. All right, so mass of water we have above. That is 200.00 grams. The specific heat of water you can find in reference table in your chemistry data booklet is 4.18. The temperature change that occurred here is positive 13. Go through and do your calculation, and you get 10,868 joules. All right. At this point, you could convert it to kilojoules because the problems usually ask it for kilojoules. It doesn't matter. But all we have found right now is how much energy the water had absorbed. Okay, so the next part we want to do is calculate the energy of the fuel. Okay, so what we're going to do here, remember, the delta H of the reaction equals the negative delta H of your water, which we found. So the way we do this is we are going to take that change in water and divide it by the moles of substance we burned, which is why we calculated the moles of the substance. Okay, so now we have negative 10,868 joules. We're going to divide that by 0.00976 moles of fuel burned. You will get negative 1.11354 joules per mole. That's an ugly number, so we're going to turn that into kilojoules. So that's negative 1.113 kilojoules per mole. Do not forget your significant figures. If you forget how to do sig figs, please reference the video on how to do significant figures. But the way, or the rule of thumb, is the lowest sig figs in the information given to you is how many sig figs you have to produce. Going back, you had 200.00 grams. That was 5 sig figs. 13.00 degrees Celsius, 4 sig figs. 0.45 grams, 2 sig figs. So your answer needs to be in 2 significant figures. So negative 1100 kilojoules per mole is the correct answer. Now, in the data booklet, if you go in and look, has negative 1367 kilojoules per mole. Why is there a difference? Okay, so this is where the errors come in, and you will be asked to discuss errors. Well, it's a combustion reaction. You could have incomplete combustion, right? So incomplete combustion means you're low on oxygen, especially if it's a really closed system. So not all of the ethanol actually reacted completely. So you could have an incomplete transfer of energy. Where would it have gone? Could have stayed in the copper collimator. It could just be hanging out in the atmosphere. The water could have lost some. We don't know that. And this was not done under standard conditions. Again, really hard to control. It may not be a 100 kPa. That's not happening for us here in Colorado. It may not be at 298 Kelvin. We cannot control the temperature in our classrooms. So there are reasons why this may not work. All right, so we looked at the enthalpy change of combustion. Now we're looking at the enthalpy change in the reaction of a solution, because most reactions in chemistry actually occur in solution, including in your body where most reactions take place, right? Okay, so looking at a solution. Again, this still needs to be carried out in an insulated system. And again, we're going to calculate that reaction, the delta H of reaction, by the change of the delta H of water, because we can directly measure the water. So this setup, you're going to get a polystyrene cup, styrofoam cup. We actually have these really big tubs we use that are insulated. So we have these tubs that you put our polystyrene cups in. These tubs have foam, so it's an insulating layer. Then you have your polystyrene cup. Which is a really good, again, insulator. Inside, you're going to have your aqueous solution, right? Here's our aqueous solution. In that aqueous solution, we're going to put a thermometer. On top of all this, we are going to put a lid so that we try to reduce how much gets released into the atmosphere, okay? And so by insulating, we're hoping to trap any of the heat from the surroundings, trying to keep it into the cup to the best of our ability. Now, why we can calculate the delta H of water in a solution? Well, most of our solutions, right, are very dilute, which means the water is really what we are measuring, because the likelihood of us measuring a change in the actual reaction in the compounds itself, very unlikely. All right. There are several ways that this can be solved. So again, read the question incredibly carefully, or read the lab incredibly carefully. So here we have copper aqueous. So really this is a copper sulfate solution. We are going to throw some zinc pellets in there, and because zinc is more reactive than copper, copper comes out of solution as a copper solid, and you get a zinc aqueous solution. So we have this going on, and we are using a probe to look at the change in temperature. So we are going to get a graph. All right, so we are going to have, here's our temp, so degrees Celsius. Here's the time that's taking place, right? So we are going to be measuring the copper sulfate solution. Measure, 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 right? Now we're going to throw in some zinc. Sweet. So we have our baseline. We're going to throw some zinc in there. All right, we're going to see our temperature go up. And then we're going to start to see it drop again, because we're going to be losing heat to the surroundings. All right. Now you see this little curve and you're like, okay, what am I going to do? Where is it at? Well, this highest value right here, that's what we're looking for, okay? This is what we're going to record. And we are actually going to extrapolate that past our x-axis. Okay, the reason we do that is the reaction started when we added the zinc. But because it takes time for those reactants to find each other, so on and so forth, and for energy exchange and for our thermometer to read it, there's so much going on, we don't get the immediate temperature release. So we extrapolate that line to find the temperature the moment the zinc, oh my goodness, the moment the zinc showed up. All right, so we are going to look at the max temp that reached upon reaction. Okay, so because we're going to start to see heat loss as soon as the reaction has taken place. So we have our extrapolated line. Now this extrapolated line assumes the same rate of cooling. We have no other way to do that. So we need to assume that the cooling is going to take place. So we have this line, we have this graph, we can extrapolate the data. You will have to do this, so make sure you're able to read the graph so you can extrapolate backwards, and then you find that point in which zinc was added for the temperature that takes place during that reaction. All right, so how do we actually go through and figure this out? So just like before, we have our delta H of our reaction equals negative delta H of the water. As we have learned that delta H of water needs to be divided by the moles of the reactant to find the effective moles of that reactant on the reaction. All right, because we're working with a solution, right? You want the moles of your limiting reactant. This will either be given to you from the concentration of the solution, or just note what is in excess of the solution, so on and so forth. So like the zinc pellets are in excess, so on and so forth. Now, we are working with solutions. So you need to go back and remember molarity. Molarity's calculation is the concentration equals the moles of your solution or of your substance over the volume. And that volume needs to be in liters, all right, or in decimeters cubed. So again, liters to milliliters is the same thing as decimeters cubed to centimeters cubed. Because we're not going to be working with liters in the volume of a reaction, we're going to be measuring milliliters or centimeters cubed. The molarity is given to us in liters or decimeters cubed, so make sure you are keeping track of what is what units you are working with, when and where. Okay, so what you need to do and what you need to keep track of, what information is given to you and how do you go through and solve this. If there's enough information given to you, I would solve for moles from the concentration calculation and then just plug that into your delta H calculation. If you don't have a lot of information given to you, you're going to need to manipulate the calculation. All right, so I'm going to go through and manipulate this because we want moles. So remember, moles is symboled as N. So if we have, let's say, moles of copper sulfate from the previous example, right? That's going to equal the concentration of copper sulfate times the volume of copper sulfate. Remember that volume is going to have to be changed. So you're going to want to divide that volume by 1,000 so it goes back to centimeters cubed. Now we know in our reaction, for our delta H of reaction, It's negative the mass of water times the specific heat of water times the temperature change of water, right? And we are going to divide that by the moles of copper sulfate in the solution. All right, so now you're like, well, depending on what's given to you, you may not be given a lot of information. You're like, well, I don't actually know how much copper sulfate I'm using, right? How am I supposed to know that? Well, there's a big assumption you can make. And a big assumption is the volume of your copper sulfate equals the volume of your water, because we really can't differentiate the two. It's such a dilute solution, and therefore volume of water can also equal mass of water, right? Because it has a density of 1.0 grams per centimeter cubed. So because water has 1 gram and per centimeter cubed, that means 1 gram of water equals 1 milliliter of water. Therefore, if you're given mass of water, you can be given volume of water. It's the same number, which means it's the same number for the volume of copper sulfate. All right, so I'm going to plug in some information here. So we have the negative mass of water times your specific heat of water times the change in temperature of water. Because we do not know moles of copper sulfate, because we do not know volume of copper sulfate, we can go through and say that the concentration of copper sulfate times the volume of copper sulfate, remember that divides by 1,000. All right, well, mass of water and volume of water equals the volume of copper sulfate. Therefore, mass of water goes away, volume of copper sulfate goes away. All right, so then that means you have specific heat of water times the change in temperature of water divided by the volume or the concentration of copper sulfate divided by 1,000. Well, because this was originally in joules, well, let's get rid of that 1,000 and it becomes kilojoules. And here is the calculation you need, right? So now we are ending up with the negative specific heat of water times the change in temperature of water over the concentration of copper sulfate. You never have to go through this process of simplifying this reaction if you just remember what can be done. But I have seen numerous times where IB gives you certain information that you have to manipulate your calculations. So if you cannot memorize the calculations, please learn how to manipulate them. If you need help with that, please come see me, because it happens over and over. All right, so let's say in our problem, we have a reaction of copper sulfate with excess zinc. We know our concentration is 1.0 moles per decimeter cubed. Because we got rid of that 1,000, we are good. The change in temperature, we are going from 20 degrees Celsius to 70 degrees Celsius. The specific heat of water, 4.18. All right, so go through and plug in. The negative specific heat of water, 4.18, times the temperature change, so final minus initial, 70 minus 20 gives us 50, divided by the concentration. We get the delta H of our reaction is negative 209 kilojoules per mole. It is an exothermic reaction because that is all that was given to us. Now, more information could be given to you, such as the mass of the copper sulfate used to make the solution or the volume of copper sulfate used in the reaction. Different information can be given to you. I gave you the hardest one. so that you could go through and see how reactions are going to be manipulated.